Section 10.3 Inferences for two population means, as we did in the previous section, using independent samples, same way as in the previous one. Here, with the standard deviations for the two population, it's assumed they're not the same. That's the only difference. But this changes a lot of stuff here when we start working with testing. Now, when we had the sigma 1 equals sigma 2, algebraically, when we came up with the formula for the t-statistic or t-test statistic, it helped a lot there. But since these are not the same, we can't, what we did in the previous section, which I didn't show, but that's where the formula came from, is by factoring the common sigma square out. But here we can't factor, so we have different formulas to deal with, and all they have to do is, we're still doing t-statistics here, and the conditions are the same. X is known distributed for two population means, independent samples with sizes n1 and n2. Then the t-statistic is is x1 bar minus x2 bar, as you can see, divided by the minus all that stuff that is eventually going to be 0, divided by s1 square and over n1 plus s2 square over n2. So s1 and s2 are the sample. So you have sample 1. Sample 1, it has size of n1. Sample standard, let's write down. Sample standard deviation is s1. That's what s1 is. And then with mean x1 bar. And sample 2 would be the same thing. So instead of using, because these are not the same, what we use here, we're using a t-statistic here, and we don't know what this is. This is not known. We don't know what that is. So that's why we're using the sample standard deviation. Also, we did the same thing in the previous section. We use sample standard deviation. So, but here we can't take it out. Like in the previous section, we took these two outside. That's why we get S sub P, the pooled standard deviation. But we can't do it here. And then the degrees of freedom, that's the one that looks scary here. It has this formula. They use the capital letter delta for that here. So, but we do not want you to calculate this by hand, or but I'll show you a shortcut on the calculator how you do this to get the degrees of freedom. After we get the degrees of freedom, that will help us to find the critical values, work with table 4, and as you know from before. So in general, so if we need to set it up, the conditions need to be met that it's a simple random sampling, independent samples, and the normal population should be normally distributed or bigger than or equal to 30 for the sample sizes. The fourth condition is not here. That was that the mean standard deviation for both sample, for both populations, should be the same. Here it's not. They are not. We know they are not. Setting up the hypotheses is an easy thing to see. You know, alpha is the level of confidence, and this is the t-statistics. The only thing is gone is mu1 minus mu2, as you can see on the top of the page, the highlighted part. That's gone from the null hypothesis, from this part here. So let's see what they usually give us to work on a problem. Let's look at an example here. They give us two samples. The first one has a mean of 394.6, sample standard deviation 84.7, and sample size of 14. For the next one, x2 bar, s2 and 2 is 468.3, 38.2, and 6. What we need to find here, we need to find the test statistic t. So they give us x1 bar, x2 bar, they give us s1. So everything is given. All we have to do now is just substitute them in. So we're going to substitute the values in to get the t statistic. That's 394.6 minus 468.3 over the square root of s1 square, which is 84.7 square, over n1 plus 38.2 square over 6, and and I'm gonna put that in the calculator, rounding to 3 decimal places. Is given as we found to 3 decimal place negative 2.681. That's t sub 0, t statistic value. Now if we need to find the critical value, we need to check first what is this given. Assume it is a left tail test. It will be given in the problem. It's a left tail test, and alpha, assume alpha is given as 0.05 or 5%. So we are going to find the degrees of freedom first. This is the hardest part of the calculation. So what I'm going to do, I'm going to write down the steps about how to, on a TI 84, 84 plus, or 83, how you can key in the numbers. How can you find this? First thing you go, so I'm gonna write calculator. First thing you can do is you need to click on stat and then go to tests and then scroll down to to sample t-test. Then go to, we don't have a data given. You see the input is either a data or stats. It's a stats. Stats means the information they give us up there. And hit the enter key. Then you're gonna enter the data in x1, sx1, n1, x2, sx2, and then scroll down to where it says mu1. So mu1, you're gonna use the arrows to go to the middle one. That's where it's less than mu sub 2 because it's left tail test. And then this is non-pooled. This is non-pooled anymore. Non-pooled. So you're gonna, under the pooled, you're gonna say no. Hit the enter key and then calculate. Scroll down to calculate and hit the enter key. It will give you the degrees of freedom. Degrees of freedom is 17. Well, it says 17.827 something something. We always round down to the next integer. And in mathematics, that's called the floor function. So we round down to the lowest integer, which is 17. Okay, so we got this one. And we need to, because it's a left tail test, we're gonna go to find negative t sub alpha. Negative t sub 0.05. With this degrees of freedom and this on the table 4, I found out the critical value is negative 1.740. So that's what we found. So graphically, like if you want to see it on the graph, what that means, this is 0 here, negative 1.740. And this is the area. The area was the alpha, which is 0.05. That's what we have it here. This is the critical approach. And to see if we need to reject the null hypothesis or not, we need to go back and check what we got for here. Degrees is 17. We got this one for T0. Where does it fall? Negative 2 point something. Well, it's somewhere here. Negative 2.681. So since that T0 falls in the rejection region or critical region, we reject the null hypothesis. We reject the null hypothesis. And this is the t-statistic or the critical value approach. How about the p-value approach? So I'm going to show how the p-value approach works. to do that, how do we find the p-value? We found already t sub 0. It was negative 2.681, and they give us alpha 0.05. We are going to find the p-value. So remember, the p-value is always the probability, or the area is the probability, right? Is the probability, you know, that with the given t value. And don't forget the degrees of freedom, we found 17. And what I'm gonna do is look on table 4, and if you remember, table 4 has a look at the degrees of freedom 17, and look for a value that is negative 2.681. You're not gonna find the negativity, but by symmetry we can look at the 2.681. And by looking at this, I do not see that exact value there. So like, it doesn't mean something wrong or there's no solution to this. But one more time, we're gonna look at this right now. That falls between two numbers, 2.567, between this number and the other one, 2.898, like that. So then what we do, we look up here and see what these values are. You will find, so this is the actual p-value that we want, but we can't find what that is. So we look at it, it falls between 0.005 and 0.01. That's what the p-value is. What's the p-value? Well, the p-value, the probability, is between 0.005 and 0.01. Okay, so that's the p-value. Now we're gonna compare it to alpha. This is alpha. So note that the p-value, it's less than alpha. So since it's less than alpha, we reject the null hypothesis. We reject the null hypothesis. This means we have really strong evidence against the null hypothesis. So that's what we mean by we reject the null hypothesis. The last thing to talk about again is the interval, confidence interval for mu1 minus mu2. How do we calculate this? Well, it's almost the same formula as we did before, but it's kind of x1 bar minus x2 bar plus or minus t sub alpha over 2, the square root of s1 square over n1 plus s2 square over n1. And notice there's no sp in there because the s and s1 square and s2 square, they stay inside the radical sign. So if we need to run obtain 90% confidence interval for mu1 minus mu2, the way we do this is that 1 minus 90% is 1 minus 0.90, 0.10. That's alpha. That's our alpha. And what we need to do is to find, because t sub alpha over 2. So t sub alpha over 2 is t sub 0.05. And from the table, and I found this earlier, from table 4, it's 1.74. Okay, so what is given? This is given. They give us n1, n2. We just found this one. S1, S2 are also given. All we have to do is substitute them in. So that gives me 394.6 minus 468.3 plus or minus 1.74, the square root of 84.7 square over 14 plus 38.2 square over 6. And you can split it one time positive and one time negative. And calculation wise, I got 121.5 and negative 25.9. So the interval is from negative 121.5 and negative 25.9. That's what we got. This means we are confident that the difference between the mean the two means that we have. Okay, it's somewhere between negative 121.5 and negative 25.9, whatever this talks about, if it's minutes, it's time, or something else. So that's what this tells us. This is what this section is about. So we did it for, if we did it for two-tailed test, it would be the same for left-tailed test, would be the same for right-tailed test. So just less than, bigger than, less than or equal. So that's what this section is about. So it's all the same, almost the same. It's just the way we approach it is sigma 1 or the population standard deviation known or not? If they're known, what do we do? If not, are they equal or not? Well, in the previous section they were equal, but here they're not equal. And so when they were equal, we used the pooling test to run the testing for the hypothesis. Here is the non-pool t-test. The other one was pool t-test. Here, sigma 1 and sigma 2 are not the same, and then we use non-pool t-test. And the example I did was for left-tailed test. Same thing works for right-tailed and two-tailed test. And you can always check these graphs. So I use this one. The right tail will be the same. Keep in mind they are symmetric. That's what the normality of distribution means. But if you do the two-tail test, you're going to run it this way. You're going to run it this way by paying attention to the alpha and the t sub alpha over 2. These are the formulas that I used. I did not, as you notice, I did not put the numbers into the calculator one at a time. That will take a lot of time and easy to make mistakes. But rather we use the calculator to run this. Most of the time they don't give you data, they just give you the values, values like this, okay, like this. This is called statistic. But if they give you actual table value, then when you hit the stats, right before stats you use data, and then you have to key in the data into the calculator. So that's what this is about.